Hi guys, here is MIH and welcome back to the second part of the series. In the first part, we covered the synthesis of chloro, bromo, iodo, and aqua complexes of pentaamminecobalt 3. In this video, the remaining 5 complexes of amine, carbonate, thiosulfate, nitrito, and nitro will be showcased, as well as the characterization of the 8 complexes. The amine complex, hexaamminecobalt 3 chloride, was one of the most famous and popular cobalt 3 complexes, but its synthesis happened to be quite difficult to tackle for me. For my first attempt, I mixed 7 grams of cobalt 2 chloride hexahydrate with 5 grams of ammonium chloride and 6 ml of water, and added 0.2 grams of activated charcoal as a catalyst. 13 ml of concentrated ammonia is then added in, and air is blown through the mixture for around 4 hours. But in the end, all that's left is some weird pinkish compound, probably the aqua complex mixed in with remaining ammonium chloride salts. The second attempt was done at a slightly bigger scale, but the result is similar. However, my third attempt that used hydrogen peroxide as an oxidizer instead of air was successful. The key is to heat the mixture to 60 degrees C for an hour after completing the oxidation, to facilitate a ligand exchange between water and ammonia. The mixture is then filtered, and the residue is mixed with 50 ml of water along with 1 ml of hydrochloric acid and filtered again. The filtrate this time shows a bright yellow color. 20 ml of hydrochloric acid is then added along with some ethanol to precipitate the product. The yield was tiny at 0.14 grams, but at least I finally had some yield. Next up, I tried making the carbonate complex, pentaamminecarbonatocobalt 3 nitrate, but failed. I dissolved 100 grams of cobalt nitrate hexahydrate that I made myself with 50 ml of water and added a solution of 123 grams of ammonium bicarbonate dissolved in 150 ml of water, as well as 250 ml of ammonia. The original procedure called for ammonium carbonate instead of bicarbonate, and I think the failure lies here since ammonium bicarbonate has a lower solubility and cannot reach a high enough carbonate concentration. Anyways, air was blown through the mixture for 22 hours, and the crystals were filtered. Everything seemed okay, but when I tried to recrystallize the salt with water, the color of the product was a dark pink instead of the light red-brown in literature, so I think I've got a bunch of aqua complex nitrate salt. This failure hurts a lot since I used up a lot of chemicals, and the carbonate complex is a key starting material of other complexes that I plan to do. For example, adding acetic acid to it would easily afford the acetate complex. But anyways, I proceeded to one of my remaining choices, the thiosulfate complex. I dissolved 10 grams of cobalt chloride hexahydrate in 50 ml of water and added 2.4 grams of ammonium chloride, 12 grams of sodium thiosulfate pentahydrate, and 50 ml of ammonia. Finally, I make up the volume with water until 80 ml. Under an ice bath, I dropwise added 30% hydrogen peroxide until I saw the color change to a deep red-purple. The temperature shot up to 60 degrees C at the end of the addition, which should be avoided with care as the thiosulfate complex is sensitive to temperature. I then tried taking a small sample of the resulting solution and adding a concentrated ammonium chloride solution, but no product precipitated. I thought I'd screwed everything up with the bad temperature control, so I left the beaker on my lab bench for a few weeks, and it surprisingly crystallized. Although definitely very impure, the crystals show a dark red color consistent with the literature, and that's all I need. The final 2 complexes I'm making is nitrito and nitro. They are the first observed case of linkage isomerism. The only difference between the two is whether the oxygen or the nitrogen in the nitrite group is binding to the cobalt. Their synthesis is also nearly identical. I start by dissolving 10 grams of pentaamminecobalt 3 chloride in a mixture of 25 ml ammonia and 150 ml of water under slight heating, and neutralize the resulting solution with hydrochloric acid until pH equals 6. This is just to prepare a solution of pentaamminecobalt 3. 10 grams of sodium nitrite is then dissolved into the solution, and 10 ml of 20% hydrochloric acid is added. The mixture is cooled with ice for 20 minutes, and reddish-yellow crystals of the nitrito complex begin to appear, which I separate with filtration and wash with ethanol. To make the nitro complex, I simply added 12.5 grams of sodium nitrite instead of 10, and didn't add the hydrochloric acid. A yellow precipitate of the nitro complex appeared, and I filtered it off. The 2 complexes have a visible color difference, as the nitrito is more orange while the nitro is yellow. However, the nitrito complex transforms to the more stable nitro complex on standing, which caused some interesting results in the spectroscopy later. Now I have samples of all the complexes. It is time to measure their absorption spectra with a spectrophotometer. I weigh out 0.01 grams of each complex, dissolve or suspend it in 6 ml of water, and add a portion of this solution to a PMMA cuvette. I then place the cuvette in the spectrophotometer and record the data with the Logger Pro software. The spectrophotometer is able to record wavelengths ranging from 380 to 900 nanometers, which is very handy. After the measurement, I then diluted the complex solution to 12 ml and 25 ml respectively, and repeated the measurements 2 more times. A peak absorption wavelength can be obtained from each absorption spectra, and the average absorption wavelength of the 3 samples is plotted against the pKb value of the ligand. The calculation can be seen in this table. As you can see, there is an apparent linear relationship between the pKb values of the ligand and the maximum absorption wavelength of their respective pentaamminecobalt 3 complexes. In fact, my correlation is even better than the correlation of the literature values, shown by my data's larger R-squared value. This relationship is due to the field strength of the ligands, and is sort of complicated since it features the ligand field theory and some stuff about orbitals. But briefly, the ligands having stronger field strength interact stronger with the d orbital of the central cobalt atom, causing the energy difference between HOMO and LUMO to increase, and thus the absorption energy of light also increases, which implies that the wavelength decreases. The field strength of ligands is difficult to quantify directly, but has a relationship with the ability for the ligands to bind to hydrogen ions, which can be reflected by the ligand's pKb. But all in all, there is a positive correlation between the ligand's pKb values and their maximum absorption wavelength of the complexes, proving that my experiment is successful. Hopefully I get a decent grade on my IA, and see you soon!